Okay, these two videos on buffers are both quite good, but this one takes too long and this one goes into too much detail. So the reason they're there is they're actually quite good, but I'll get you to watch those by yourselves. We're going to be talking about buffers. Now, we've been spending a fair amount of time talking about Le Chatelier's principle, acting between an acid and its conjugate base. We actually set this situation up in class. We've made this particular buffer. It contained acetic acid solution, and we put in the actual salt of sodium acetate. So we put those into the solution, and we actually have both of those in the water at the same time. Now, when a strong acid is added to it, like hydrochloric acid, the H plus ions have an increase in concentration, and according to Le Chatelier's principle, an H plus ion will join on to the end of this acetate ion and make the acetic acid molecule and use up the extra H plus, or nearly all of the extra H plus. And the result of that is that the concentration of the H plus doesn't actually change very much, so that the pH, which depends on the concentration of the H plus, won't change very much either. So it's protected from that little change, that little addition of acid to this. In a similar way, if we put OH minus with this, if we put some sodium hydroxide with it, the OH minus reacts with the H plus and just makes water. So that's going to actually take out the H plus ion concentration. So the system's going to try and remake the H plus ion concentration by breaking up this acid molecule into the acetate anion and the H plus. So it's reforming the H plus, and again the concentration doesn't change much of the overall H plus, and so the pH doesn't alter. As long as we have both substances in this solution, this will be a pH buffer at around about 5. And we saw that kind of yellowy colour in the solutions in class. Now, when we were doing our titration, which is the strong acid, strong base titration, you had a sudden change in the pH between, it really took a drop to go from pH 3 to pH 10. So it really doesn't matter greatly whether you use litmus or bromothymol blue or even phenolphthalein. You're not going to have very much difference in your end result. Because this is such a rapid change. So sometimes or even if we used methyl orange, this change is so rapid that it's not going to greatly influence the results in there. Now, when you're looking at one of these graphs, the pH is low here. So we must have started, because we're measuring the pH in the beaker, it must be that the acid is in the beaker and that we're adding the OH minus from the burette. And it just jumps all of a sudden. pH is neutral at pH 7, and that gives us our equivalence point where our number of moles of HCl equals our number of moles of NaOH. Now, if we have a strong acid, weak base, we get what we call a buffering zone in here, and that occurs over here where there is a much slower change in the pH. There's a sharp part of the curve here, and then there's a gentle, slow part. So here, choosing the right indicator becomes much more important. If you choose a pH, an indicator that changes at around about 5, then you'll be getting the pH to change at the equivalence point, which is 5.3, and you'll get the correct volume from your burette to work out your concentration with. Whereas, say you used phenolphthalein, you'd be getting the wrong answer. You'd be 2 mils off in your volume, so your concentration would appear to be weaker than it was. So it's important to use the right indicator when you've got one of the substances as a weak something, and this one is a weak base. Now, we've mentioned here that this is the normal sort of almost the usual pH curve, and then you've got the buffering zone over here. Now, this buffering zone, at this point here, you've got equal amounts of HCl and ammonia. Once I start adding more than that, so I'm making ammonium, and once I start adding more than that of the ammonium, I'm actually got an excess of ammonia rather, and the ammonium ion is present. So the ammonia that's being added past this point is excess, so that I will then have both these species present, hence the referral to the titrations, because that's where I'm going to be getting a buffering effect. I will have both these weak, a weak base and its conjugate acid there, and it buffers in at the region of around about pH 8. So if I want a buffer of pH 8, I'll want some ammonium chloride and some ammonia solution to mix together, and that will create a buffer at around about pH, if they're around about equal. The equivalence point at 5.3 is when the number of moles of acid is equal to the number of moles of base. It is not neutral. And that's because it is an acidic salt, and this reforms the H3O plus ion. Now, you could start with the acid in the beaker because you're using a data logger. You're using a pH probe or a pH meter. So really, it doesn't matter if it starts out red and goes orange, because you're not actually relying on a color change here. So if you weren't using a pH probe, then it would be important to use the right indicator, and methyl orange would be that indicator. Phenolphthalein would definitely give you a wrong answer by about 2 mils. Now you get the buffering zone at the other end when you've got a weak acid and a strong base titration. And the top half of this is the normal pH curve, and the bottom half has the buffering zone. Again, the flask contains the acid, and the sodium hydroxide is added from the beaker. So it would be something like acetic acid that's in there, and you're adding sodium hydroxide to it. Your equivalence point is at around about 8.5. It's 8.7. So at this point, your salt, sodium acetate, is a basic salt, and the best indicator is phenolphthalein. notice what would happen if you chose the wrong indicator. If you chose methyl orange, you'd be turning it off down here at around about 5, whereas if you use the phenolphthalein, you'll be turning it off at 10. So your actual equivalence point is here at your end point. If you did it with the wrong indicator, you would be using far too little sodium hydroxide, so your volume would be too small and your concentration, too large. Oh, I've been awake too long. Okay, so the buffering zone is occurring in here. And if you think about what's happening, you're starting out with the acetic acid in there, and some of it's being converted to sodium acetate, which means that we've got that situation occurring here where you've got the acetic acid and the sodium acetate in the same beaker at the same time, and some of it's unreacted. So the result of that is that you're buffering in at around about pH 5. So that's as that first image showed us. So during a titration, you've got a buffering zone if you've got either a weak acid or a weak base. Or even when you've got them both, you can have a buffering zone here. Now, when you've got a weak acid and a weak base, like acetic acid and ammonia, it should come out with an equivalence point of around about 7. With different acids and bases, you might find that it shifts either side of that. But it would be terribly hard to find the end point in this reaction because there's no sharp curve in there. There's no sharp change. And here, even though it's pH 7, this is where it does become important that you not use litmus, but that you use bromothymol blue, because litmus will change between 6 and 8. And that is a 2 mil difference in your answer, which is a big difference in your concentration. Whereas if you chose the bromothymol blue, it would go off at around 10. So you'd be much better to do that. And you've got buffering in here with the acetic acid and the acetate ion buffering in this zone here, and you have the ammonium buffering zone over here. So even while you're doing a titration, you have got a buffer being created if you've got a weak substance in there. And just to show you that not every proton transfer reaction has to take place in water, if I get a cotton wool, and I used to do this, but it's become quite hazardous, the ammonia solution, it could be soaked with on that cotton wool, and on that cotton wool, if I had strong hydrochloric acid, and I put a rubber bung into the end of the tubes and I left it for a long time. Usually this is around about 1 meter in length. You would find that there was a ring of white powder inside the surrounding the glass where these two gases meet. And so this reaction doesn't actually involve water at all, but it does involve a proton transfer of a hydrogen from the hydrogen chloride molecule and the ammonia molecule. So this one's going on to here directly. I'm leaving heat of neutralization to the end of the unit. We've really looked at buffering, and when we've looked at buffering, we've looked at the fact that even during titrations, there can be a buffering effect. And that buffers occur when you have got a weak base with its cation or a weak acid with its anion. Or you can get a pH 7 buffer, which occurs when you've got the sodium dihydrogen phosphate and the disodium hydrogen phosphate, and you'll see that in class. Okay, ladies, I hope that that clears up the connection between equivalence points, buffers, and the choice of indicators and pHs.